Hello statistics students, my name is Emigh, and this video is our discussion on section 5.2, title Binomial Probability Distributions. We have an if statement here. 1. If a procedure has a fixed number of trials. 2. The trials are independent of each other. 3. The probability of success in one trial remains the same throughout all the trials. And 4, and I think this one's the big one, each trial has outcomes that can be classified into two categories, commonly referred to as either success or failure. If all of those conditions are met, then the data has what we call a binomial probability distribution. I think of the two categories, those being success and failure, as binomial, bi meaning two, those two categories. If we do have a true binomial probability distribution, then we will be using a program called the binomial calculator. So a few steps to get through it here, which I'll show you how to do, but then ultimately the program right here is called binomial. It's going to ask us for lowercase n, and we're going to need to make sure we enter that as a whole number. And we know lowercase n is the number of trials. It's going to ask us for lowercase p, that would be the probability of success in one trial. We know that has to be a value between 0 and 1, so make sure to enter it as a decimal. The program does not want us to enter fractions. Then we will be asked, the program will ask us to select an equal or an inequality from this list here. And the way we are going to select that is dependent on the wording in the question. And finally, we'll have to tell the program x as a whole number, and x is going to represent the number of successes. Then we'll compute that, and it will give us some information on the output screen. Let's try one. Given a 0.85 probability that a randomly selected adult knows of Twitter, find the probability of getting exactly 3 adults who know of Twitter when 5 adults are randomly selected. All right, so think about that. You randomly select 5 adults. What's the probability that exactly 3 of them know of Twitter? All right, first we got to think, does this procedure result in a binomial distribution? The answer is yes. Check all the conditions. 1, there's a finite number of trials. It's 5. 2, each trial is independent of the other. One person's knowledge of Twitter would not affect the next person's. 3, constant probability of success, which is 0.85. Must have this from some past study. And 4, the 2 possible outcomes could be categorized as they know what Twitter is or they don't know what Twitter is. So we do have a binomial distribution, and that will allow us to use the program called binomial under calculator in StatCrunch. When we open this program in StatCrunch, it is going to ask us for lowercase n, so that will be selecting 5 adults. It's going to ask us lowercase p, which is 0.85, probability of success in each trial. And then it's going to ask us to set up the notation here. Capital P for the probability of, and x being, and we have to set this part up here. We're going to choose an equal sign because of this wording right here. It says exactly 3. So that would be x is equal to 3. So that's why we're going to set up the notation like this. We'll hit compute and read our output screen. Let's give it a try. Okay, once we open StatCrunch, there's no data here. This program does not run off of data in each column, but rather we go to Stat, Calculators, Binomial. Open that, And the input screen has some old information from whenever I happened to use it last. We need to change this information. We want our N to be the 5 sample size, 5 randomly selected adults. Lowercase p is the probability of success in each trial, which is 0.85. And then we need to set up our notation here. And the wording was in the question, what is the probability of selecting 5 random adults and exactly 3 of them knowing of Twitter? So exactly means we change this to an equal sign and here a 3. Okay, so we've entered N, P, our symbol, and X. When we hit compute, the probability will populate in this cell right here. We're not really using the graph for this, you guys. We're using what populates right here in this cell. So we hit compute, and it turns out the probability of randomly selecting 5 adults and exactly 3 of them knowing what Twitter is 0.1381. Now writing that into our notes, we have the probability of getting exactly 3 out of 5 is 0.138. All right. How about exactly 4 out of 5? What would the probability be if we randomly select 5 adults? What would the probability be of getting exactly 4 that know of Twitter? So let's go back to StatCrunch. And we're going to run this the same way, same program, except what I'm trying to get you guys to do here is practice what changes. For the first task, it was 3 adults, exactly 3 knowing of Twitter out of 5. And here it's exactly 4 adults knowing of Twitter out of 5. So what changes? The N, the P, or the X? The answer is N remains the same. It's still 5 adults. Probability of success in each trial is still 0.85. It's the X. When they say exactly 4, we need to run the program with probability of X equals 4 for exactly 4. We'll hit compute and we'll get our answer. Here we are back in StatCrunch. We're going to make that one change, hit compute, and that probability is 0.3915, 0469. Going back to our notes. We would write that in as the probability of getting exactly 4 out of 5 is 0.392. How about at least 1 out of 5? What would the probability be of selecting 5 adults and having at least one of them know of Twitter? Okay, the first 2 tasks were exactly 3, exactly 4, and this is changed now. It's not exactly 1. So we're going to have to use an inequality to represent at least 1. So when we run this in StatCrunch, we're going to keep N as 5, lowercase p is still 0.5058. 85, my apologies, but the notation has to represent at least 1. That would be capital P, open parentheses, X is greater than or equal to 1. And then we'll hit compute. Let's see what. Here we are back in StatCrunch. We're going to change it from an exactly to an at least, and our X to a 1. Hit compute and we'll get that probability, which is probability of randomly selecting 5 adults and at least one of them know what Twitter is. It's almost certain, 0.99992406 looks like. Let's put that into our notes. Writing that out gives us the probability of getting at least 1 out of 5 is approximately 1.000. So that is an event considered certain to occur. What if we're asked with the probability of selecting 5 adults at random and less than 2 of them knowing of Twitter. In this case, we need to address n remains 5, p remains 0.85, but our probability of x needs to represent less than 2. So x is, we use this inequality, the less than sign, and 2, and then we run it. Let's see. Okay, here we are. We just need to adjust our inequality to less than 2, run it, and we get 0.0022275. Now writing that up in our notes would be the probability of getting less than 2 out of the 5 is 0.002. All right, I'd like you to pause the video and try these 3 examples. Welcome back. Let's see how you did. Number 1, use the binomial probability program to find the probability of x many successes given the probability, lowercase p, of success on a single trial. Round your final answer to 3 decimal places. So we have n equals 12, x equals 5, and lowercase p equals 0.25. If you ran your program with n is 12, p is 0.25, and you have to make sure your notation looks like this here, capital P, open parentheses, x equals 5, and hit compute. If you ran that correctly, you'd get 0.103. Let's see how you did on number 2. Find the probability of 2 girls in 8 births. Round your answer to the nearest thousandth. So if you use the program with n equals 8, lowercase p is 0.50 here. We know that. The probability of a birth resulting in a girl, 1/2. Probability of a birth resulting in a boy, 1/2. Probability of flipping a coin and getting tails, 1/2. Probability of flipping a coin and getting tails, 1/2. That's where this 1/2 or the 0.50 came from. If you set it up as x equals 2 and ran the program correctly, you'd get 0.109. And finally, for the third one, if you did that one right, you got it set up as n is still 8, p is still 0.5, and the wording was at least 2, so you want to run it with x is greater than or equal to 2, and that would give you 0.965. If you got them all, nice job. If not, make sure you could get them in the future should it be an assessment in which you can't use your notes on. Binomial distribution formulas. So we were using the spreadsheet program, and now we're going to look at some formulas that need to be done by hand without using the spreadsheet. First one is, if we have a true binomial distribution, then the mean is equivalent to n times p. The standard deviation is equivalent to the square root of n times p times q. The minimum usual value is mu minus 2 sigmas. The maximum usual value is mu plus 2 sigmas. And for all of these formulas, lowercase n represents the number of fixed trials. Lowercase p is the probability of success in one trial. We're used to those, n and p. Q, we've seen less. Q represents the complement of P. That would be the probability of failure in one trial. Let's use these formulas for this example. For a binomial distribution, n equals 1070, lowercase p is 0.88. Find the minimum and maximum usual values, round to the nearest hundredth. All right, to find the minimum and maximum usual values, we're going to use the formula mu minus 2 sigma. This formula requires that we know mu, which is n times p. So in this case, 1070 times 0.88. Minus sign 2 comes from the formula, and then sigma turns into the square root of n times p times q, which is 1070 times 0.88, and q is the complement of 0.88, which is 0.12. If we type that in and run it correctly, we get a minimum usual value of 920.34. We're going to do the same thing for the maximum. We're just going to input that into our calculator with a plus 2 standard deviations instead of minus. So this is what we need to type in. If we do so correctly and run it, we'll get a maximum usual value of 962.86. Next example, on a multiple choice test with 11 questions. Each question has 4 possible answers. One of them is correct. For students who guess all 11 answers, find the mean or the average number of questions that they will guess correctly. Okay, this is a binomial distribution. We have a fixed number of trials, which is 11. The probability of guessing correctly on each question is 1 out of 4. Because see here in the wording, it says each question has 4 possible answers. That would be lowercase p equals 0.25. So we're going to use the formula mu equals n times p. Our n is going to be the 11, and lowercase p is 1 out of 4, or 0.25, which means that a student who guesses all 11 answers on this type of assessment would get 2.75 on average of those questions correct. One more example. McDonald's has a 95% recognition rate. Find the mean and standard deviation for how many people recognize McDonald's if a group of 12 people are randomly selected. All right, we've got a binomial distribution here. So we'll use the average number that would recognize McDonald's would be 12 times the 0.95 recognition rate. That's 11.4. The standard deviation will be the square root of 12 times probability of success times probability of failure. Type that in correctly. It'll get us 0.75498344357. Now, we'll find the maximum and minimum usual number of people by taking the mean, 11.4, subtracting 2 standard deviations to get the minimum, adding 2 standard deviations to get the maximum. It would look like this for the maximum usual number of people, and this for the minimum number of usual people. And that means number of people out of 12 randomly selected that would recognize McDonald's. So the usual range, it's somewhere between 9.9 and 12.9. Would it be unusual or not for a particular group of 12 people to have all 12 of them recognize the brand name McDonald's? The answer is going to be no, because 12 is between these two, the max and min. It makes 12 in the usual range. So no, this would not be unusual. 12 is in the range of ordinary values. That will finish our discussion and our material for chapters 4 and 5. Thank you for being here. My name is Emigh, and I will see you next time when we discuss chapter 6.